Okay, so thank you very much. Thanks a lot for the organizers for inviting me to speak at this awesome conference. I'll be discussing some work done in collaboration with Benjamin Basso and Amit Sever, and it will be mostly based on two papers that we put out early this year and maybe on some unpublished stuff. So we'll be discussing two important observables in gauge theories, namely the S-matrix of excitations of the Clawler Flux-Tube and the S-matrix of excitations in spacetime, like gluons and eventually other massless particles that we might have in a conformal gauge theory. But actually the main object that will be the key player in this discussion will actually be what will be Wilson loops, and a particular class of Wilson loops whose contour is a null polygon, okay? So null polygon Wilson loops in conformal gauge theories is the main object that we will be focused on. So let me just briefly motivate it. Of course, this is a very important object, so I almost don't need to motivate it, but let me quickly do it. So Wilson loops are defined on a given contour, so we can think of them as the effect of taking some classical particle probe along some given contour and computing its interaction with the gauge field. And this is not any contour, but rather it's a contour made out of a sequence of null edges. So you can think that you have a classical probe moving at the speed of light, then it decides to change direction, and so on until it comes back to the same point. So it's a particular class of contours. It's particularly nice to study this class of contours in conformal gauge theories, because under a conformal transformation, a null polygon is mapped to another null polygon. So this is a closed class of observables, and they are easier to parameterize compared to the more general Wilson loop, which is parameterized by a general smooth curve. So these guys, they are parameterized by the position of the cusps. If I give you the position of these 6 cusps, for example, I parameterize the polygon Wilson loop. Furthermore, actually, smooth curves can be approximated by polygons with many edges, so we don't even lose that much by considering these observables. Okay, let me postpone this picture and move to the second point. In our favorite gauge theory, in what we can call the Ising model of gauge theories, the theory that we all hope to solve and from there to learn about a lot about quantum field theory and so on, Wilson loops are equal to scattering amplitude. So if we know, if we can compute exactly the expectation value of these null polygon Wilson loops, we will have access for the first time to scattering amplitudes in non-trivial 4-dimensional gauge theories, 4-dimensional scattering amplitudes. The edges of this Wilson loop are, as I said, null vectors, k1 such that k1 squared is 0, k2, k2 squared is 0, and so on. And that makes sense because the amplitude is also specified by a bunch of external vectors, the momenta, and they are null and they add up to 0 because of momenta conservation, so the polygon is closed. Okay, so studying scattering amplitudes in n equals 4 super-Young mills in a planar limit is equivalent to studying the expectation value of this particular class of Wilson loops. Now, a Wilson loop, as we said, is given by the interaction of a classical particle with a gauge field. So here you can think that you have a quark going to the future, and here you can think the quark is going to the past, or the anti-quark is going to the future, and it's interacting by exchanging a gluon. And then at 2 loops, it will exchange 2 gluons, or a gluon would self-interact, and so on. And here it's some example of a diagram in the planar limit that we will always consider, where we have many, many gluons exchanging, interacting, and so on. Now, the net effect of summing all these interactions of gluons and actually other particles in the case of theories like n equals 4, the effect of summing all this stuff is effectively the same as thinking in terms of a flux tube that is stretched between this quark and anti-quark, and this is the net effect of all this junk. Now, the flux tube here, we depicted it as some little bump and not like some stretched tube. Now, why is that? Because a stretched tube would be what I would draw if I would have just these 2 null lines, so this quark-antiquark moving at the speed of light with some flux tube in the vacuum between them. But because there is some disturbance here in the past, because we put this cup here and because we put another cup here at the top, actually the flux tube that will be flowing will not be flowing in the ground state, but rather in some excited states, and we should sum over all possible states of the flux tube. Okay? Again, this is a cartoon. Right now I only want to give the big picture, and later we'll try to write some precise formulae. Okay, very good. So basically the idea is to relate these 2 important objects. One object is the 4-dimensional S-matrix, an object that we very much want to compute. And we want to map this 4-dimensional computation into a computation in terms of the dynamics of this 1 plus 1-dimensional toothed surface, that is, of this 1-dimensional flux tube. We want to trade it by a transition amplitude in a 1-dimensional flux tube, therefore simplifying enormously the problem, going from 4 dimensions to a 1-dimensional transition amplitude. So the goal is to make this precise. Now, this is not something very, very esoteric. It's something that we are used to doing all the time. In physics, we always sum over states. We sum over states when we compute partition functions, when we compute correlation functions. We do it for breakfast. So here is a correlation function. We have a bunch of operators, O with O. A psi1 is flowing, another operator kicks psi1, then psi2 is flowing, another operator kicks psi2, psi3 is flowing. And by summing over these eigenvalues of the dilatation operator, psi1, psi2, psi3, we would reproduce, in this case, this 6-point function. Okay? Similarly, the picture that we will present slowly in the next slides is the following. We will start with some vacuum of our flux tube between these two lines, this and this. But then this vacuum is kicked because this line, suddenly this flux tube particle decides to turn abruptly to the right. So there is a kick here. And then the state here will no longer be the vacuum, but some sum of excited states, psi1. But then these lines are again kicked here at the right by this cusp here. And now we have some psi2, and we sum over these guys, where psi2, psi1, psi2, psi3, and so on are now the eigenstates, not of the dilatation operator like here, but of the flux tube Hamiltonian. Okay? So this is the picture. Now, it's important to have in mind that these kind of OP expansions, either this or this, they have the same name because in spirit they are exactly the same. This OP expansions is not the same as perturbation theory, okay? Even though this is obvious, let me just emphasize it slightly. Of course, it's often the case that we can compute this object or this object, but let's say correlation functions at 3 level or at 1 loop or even at 2 loops sometimes exactly. In other words, it means that we can take into account all the states flowing here at 3 level, 1 loop, and 2 loops. Okay, but if we have 3 level, 1 loop, and 2 loops, we don't know much about this object at finite coupling. Okay, that's the nature of how things work. However, suppose that instead of giving you the 3 level, 1 loop, and 2 loop result, I give you the dimensions and the 3-point functions of the 100 lightest operators of the theory. And we consider correlation function of light operators as well. Then, of course, if I just sum over those 100 operators, and if I knew their dimensions and 3-point functions exactly, I would get this result with an awesome approximation. Summing 100 states would be really great. And I could plot this result, study this result at any coupling, and so on. Now, of course, strictly speaking, if I sum only over the first 100 states, if I expand in perturbation theory, I will not get the exact result, not even at 3 level, or 1 loop, or 2 loops. So, of course, these expansions are very different. If I sum over all the states, I get the exact result. If I sum over all the loops, I get the exact result. But, of course, they are not the same. Okay? So even though it's kind of obvious, let me just emphasize. Okay, so now this picture here is kind of important. There are lots of geometry here. You see there are lots of squares. I have a square where there is this vacuum, a next square where I have psi1, a next square where I have psi2, and so on. Let me explain a bit this geometry a bit slower. So the idea is the following. We will build a tessellation of null polygon Wilson loops into a sequence of squares and pentagons, as I will now explain. So now we are going to dwell into some kinematics that will make the dynamics much easier to digest later. So let's start with some polygon with n edges. And then what we do is we assume some tessellation where we take this cusp and draw the light cone and consider a null line that intersects this line at some given point. So this point, if it exists, it's uniquely fixed by the constraint that this line is null. Okay? So remember, all these lines were null, and now this is another null line that goes and intersects this line here. Then we take the next cusp, and we draw again a null line that intersects this guy, and we see that in this way, we are building, here is a square, a null square, here's another null square, and here are a few more null squares. How many squares there are? There are n minus 3 null squares. How many there are in the middle? Okay, we subtract 2, there are n minus 5 null squares. Remember, we started a vacuum here, psi1, psi2, psi3. So number of middle squares is the number of squares where interesting things is going on. And then, what joins 2 squares? Well, 2 squares are joined in a pentagon, as you see here. Here is a blue pentagon, here is the second pentagon, which is a red pentagon. And how many pentagons there are? There are n minus 4 pentagons. Okay? Now, I start with some configuration where this is the tessellation. Of course, if I start deforming a lot my polygons, at some point these lines might cross cusps and so on. This defines some radius of convergence of the OP. You can ask me more about it if you want. Okay, so here are the pentagons, and here is the main picture. Now, this is already some dynamics, of course, but let's move on. Okay, so again, I'm just giving the overview, then we will go into more detail, but then the basic picture is the following. We can write the expectation value of the Wilson loop as a sum over the eigenstates of the Hamiltonian, the Flux-Tube Hamiltonian that flow in the first square, the second square, and the third middle square in this case. And we have some transition, some pentagon, that is a transition between the vacuum and the first middle square. Then the first middle square and the second middle square, psi2, psi3, and psi3 in the vacuum. Or more generally, it's something like this. This is what takes into account the transitions. It's exactly the analog, you see, it's exactly the analog of three-point function. So here is a three-point function, here is the first blue pentagon. Here's another three-point function, the second red pentagon. So this stuff just takes into account the gluing between consecutive squares. And then in each square they propagate, and there are some nice coordinates that parameterize null polygons that are some tau I, some times tau I, some space sigma I, and some angles phi I that parameterize the geometry relative to each of these squares, as I will explain in a few slides. And all the geometry comes about in this propagation part. Okay? This is exactly, again, like in correlation functions, where we can separate the space dependence, the kinematical part, from the interesting part, which is the three-point functions, which control the dynamics. So again, it's exactly the same. So there are two quantities that we need to compute in this one-dimensional flux tube to get four-dimensional scattering amplitudes at any value of the coupling. One is obvious, this E here, the energies of the flux tube states. So we need to be able to compute the exact spectrum of the Kohler flux tube. What's the energies of all the excited states of the flux tube. Then we also need to compute this pentagon transition between two states, say psi1 and psi2. So we need to compute all these pentagon transitions between any two flux tube eigenstates at any value of the coupling. Now, this is not totally obvious that this is a property of the flux tube. You could think that there are here different pentagons. Is it too loud? No? You might think that there are different pentagons. For example, take the blue pentagon and the red pentagon. They look very different, right? I mean, they don't look the same. But actually, all pentagons are conformal invariant. So there's only one pentagon transition. So you have the pentagon transition between psi1 and psi2, and that's it. There's no information about geometry. So this is really a property of the flux tube. That's what emphasized below, here, down here. The geometry just enters here trivially in the square bracket, and then there are two quantities, the energy and the pentagon transitions. So here is the outline, the questions that we have to address. The first two are mostly dynamical questions about what exactly are these coordinates, what exactly is this tau sigma and phi, how do we parameterize polygons, null polygons. So Wilson loops are divergent. So there is a divergence that is given by proportional to the length of the Wilson loop. That one you don't have because our edges are null, so the length of our Wilson loop is 0. But there are local divergences whenever you have a cusp in a Wilson loop, and we do have a bunch of cusps, right? So what exactly does it mean to sum over these flux tube eigenstates? This looks a bit formal. How can we make this precise? And how do we compute these pentagon transitions? Well, how to make a Wilson loop that naively is very ultraviolet divergent into a finite quantity? It's actually not so hard. What you do is you consider, you see here you have two middle squares and you have a bunch of pentagons, and you multiply your Wilson loop by other Wilson loops with smaller number of edges that are also divergences, but in a way that is well thought of, such that all the divergences cancel off. Okay? So you can see that there is a cusp divergence here, but it's also here, so it cancels out. You can easily see that this guy is really finite, and it has no anomaly and so on. It's really a finite conformal invariant object. Now, if it's final and conformal invariant, it's invariant under conformal transformations. It means that it can only depend on data that is invariant under conformal transformation. What's that data? It's the cross ratios made out of the positions of the cusps of this polygon. So it can only depend on cross ratios made out of the positions of the cusps of the polygon. Now, it's easy to see that for polygons with 4 and 5 edges, there's no cross ratios you can construct. So if you have 4 edges, for example, a null square, only the diagonals have non-zero distance. You don't have enough to make a cross ratio. So only starting at 6 and 7 points, you start having cross ratios. Therefore, squares and pentagons have no cross ratios, and they are just fixed by symmetry and given by the BDS and ZATs. Exactly like 2 and 3-point functions in a CFT are fixed by conformal symmetry. So because we know them, we don't lose any information by multiplying or by dividing by them, and therefore this is a nice finite ratio to consider. What about the geometry? So you have to introduce some time, some space, and some angle that measures stuff that is flowing. Now, how do we measure stuff that is flowing from a region A to a region B? How do we measure some charge? How do we measure? We act with some symmetry generator corresponding to the charge on this half, on A, if we want to measure what flows from A to B. Of course, we don't act on everything, otherwise we get 0. If we act on everything, it's a symmetry. So that's how we measure what's flowing from A to B. For example, when we have a 4-point function, we act with the Casimir operator on 2 of the points to measure what is flowing from these 2 points to the other 2 points, and in this way we determine conformal blocks and so on. So what we should do, therefore, if we want to see what is flowing through each square and introduce some nice variables, we want to do is the following. We take a null square, here it is, and we consider and we check what are its symmetries. So what are the symmetries of a null square? What is the subgroup of the conformal group that leaves null squares invariant? And it turns out that that group is R times U1. So there is a non-compact translation in time, a translation in sigma, and the rotation of the directions orthogonal to the plane where this square is. So if we want to parameterize these Wilson loops, what we do is we go to a given middle square and we act with these symmetry generators, sigma, tau, and phi, on the cusps to the bottom of it. Not to everything, of course, to the bottom of this. And in this way, we generate a family of polygons where if we look at the term multiplying e to the minus tau, it tells me the energy flowing in this square. Okay? Just the usual stuff. How many parameters do we have? We have n minus 5 middle squares, 3 parameters per square, 3n minus 15 parameters. That's the number of cross ratios of null polygons. So this is a nice parameterization of all conformally inequivalent polygons. This is an equivalent definition. In other words, what we are doing is something like this. So we have some tessellation of polygons, you see, some sequence of null squares, and we take a given null square and we move like these carnival snakes. At least in Portugal, they are very popular. You see, you can move them like this, and they move here in sigma. You can stretch up and down. This will be moving in time. Parents typically don't like these tessellations because the first null square is a whistle. But, but for us, the first null square is the vacuum, so I'm sure they would love it. So, and so that's it. So basically what we said so far concerns mostly kinematics, and because of that, this is valid in any gauge theory, in any conformal gauge theory. And now we will specialize to n equals 4 super young Mills. But what we found so far is that we have some Wilson loop that is nice and conformal invariant and finite and so on. And it's given by some explicit geometry and then some transitions. Here I wrote the heptagon, so there is vacuum to psi1 to psi2 to vacuum. Okay? And we have to compute these two quantities, the energies, the transitions, and we have to understand what these sums mean. So there are several equivalent descriptions of the excited Flux-Tube states. So one way of describing this Flux-Tube between this quark and antiquark moving at the speed of light, the Flux-Tube is just a null Wilson line. And the excitations are just adjoint insertions along this Wilson line. So we just put, say, some field strength at some position on the null Wilson line, another field strength. We can give them some momenta, study how these guys scatter, and so on. And this scattering is nothing but governed by the Flux-Tube S matrix. An equivalent description is to think that a way to stretch to create a null Wilson line is to put many covariant derivatives in a given null direction. And then what we do is we put many covariant derivatives, then some excitation, then many derivatives, then another excitation, then many derivatives, and this is basically the same as above. So this is another description in terms of local operators, where we put some excitations, we give them some momenta, and again we can study how they scatter. Or equivalently, we know very well that an operator with a lot of spin is dual to a folded string in EDS, found by Gabser, Klebanov, and Polyakov. It's the so-called GKP string. And if we put two excitations there, it corresponds to putting two bumps of this string that move and scatter with each other. And again, the S matrix is nothing but the Flux-Tube S matrix. Now, we control these guys very well from integrability, especially from the second point of view, where we have local operators. So we know exactly their spectrum. We know the energy of these guys exactly. We even know how they scatter exactly. This was found in some recent work, more recent work. So basically, if we have, say, an excitation here, the energy is a function of P, epsilon of P, but it's useful to parameterize it as epsilon of U and P of U, so it's just a more convenient parameterization. Okay, so the states of the Flux-Tube, summing over psi, means something precise. Means you consider a state with a given number of excitations, because it turns out that's a quantum number of the system. And you have to sum over a vector A and integrate over du1 up to dun. This A just indicates what kind of particles we consider. For example, here we have two F fields, so this A is FF. Okay, this just indicates what kind of particle we sum. Fermion, scalars, gauge fields, and so on. And then we integrate over the momenta of the particles, du1 up to dun, or dp1 up to dpn, or du1 up to dun. It's just a useful parameterization. Okay, very good. So this, we made big progress, because now what was before something very formal, now it's something very explicit. We just sum over the fields in our gauge theory, like n equals 4. We integrate du1 dun, dv1 dvn, and we now have some functions of a vector and another vector, and a vector index and another vector index. The challenge is to compute these pentagon transitions. How can we compute this pentagon transition between some u's and some v's? Okay? Now, the simplest transitions and the most important transitions are obviously, what are the most important states here? Okay, let me go back one step. What's the most important state? It's of course the vacuum, where we start with the vacuum, 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 vacuum. Indeed, the vacuum has transition equal to 1, energy and momentum and angular momentum equal to 0, so it just gives 1. So it's just a Wilson loop, it's 1 plus the states which are not the vacuum. So what about the next one? What's the most important one? So here we have e to the minus energy times time. Of course, the most important states are the lightest ones, as usual. So the lightest states are the states that contain one Flux-Tube excitation, and then two Flux-Tube excitations, then three Flux-Tube excitations. Furthermore, because we have integrability, we expect that if we can study the dynamics of a few number of particles, we can get to multi-particles by some sort of factorization. So it's reasonable to expect, and it actually turns out to be the case, that if we study simple particle transitions, we can get to multi-particle transitions in a more or less straightforward way. So this is the goal. The goal is to compute a transition. Here is the simplest one. There is a particle with rapidity u, that is momentum p of u, and a particle with momentum p of v, just a transition between this particle and this particle in this pentagon. It is this single particle transition. Okay? We want to compute this guy at any value of the coupling. The goal is to compute scattering amplitudes at any value of the coupling. Okay, very good. Now, of course, u doesn't need to be equal to v. This guy doesn't preserve momentum, doesn't preserve anything. So this is what it is. And the idea is the following. The idea is to postulate some bootstrap-like axioms. So we look at this guy, we postulate some axioms that it should satisfy, and we look for a solution to these axioms. Okay? So let me just motivate where these axioms come from. But let me anticipate that this S of u and v is nothing but the S matrix, the Flux-Tube S matrix of these two guys. So we see that an object, which is the S matrix of the Flux-Tube, is appearing, governing the behavior of this pentagon transition P, that itself governs the behavior of the four-dimensional scattering amplitude. So this is the connection between the Flux-Tube S matrix, this S matrix S of u v, and the four-dimensional S matrix of the gauge theory. So let me explain where these axioms come from. Okay? Actually, this one is the simplest one. I can even explain it in this slide. If you flip u and v, of course, you get the same picture. You just should look it from the other side of the blackboard. So this is just a reflection symmetry of the pentagon. Okay? So this one is just too trivial. The other ones are kind of more interesting, so I think I have time to discuss them. So axiom 3, but I'll do it very briefly. You can ask me if you want me to go through in more detail. Axiom 3 is about weak rotation. So we know how these excitations behave in great detail. We know their dispersion exactly. And we can implement weak rotation. We can exchange time and space. We can find a transformation that interchanges energy and momentum. By exchanging time and space, if this was space and this was time, by interchanging them, the guy that was here is moving to the next edge. But this is again a pentagon transition. So we end up with some transformation that is some kind of crossing relation that tells you that if you implement a mirror transformation on your particle, you also get another pentagon. Thanks. The last one is the statement that if you exchange two particles, you pay an S matrix. This is kind of a fun one that a priori we were a bit confused about, because you see, this particle, one is incoming and the other is outgoing, and we have a transition between this guy to this guy. There's nothing to scatter. What does it mean to exchange the incoming and the outgoing one and pay an S matrix? The particle is just going from the past to the future. There's nothing to scatter. Where is this S matrix coming from? But actually, it turns out, it would be much more natural if both particles were incoming or if both were outgoing. Then it would make sense to exchange them and pay an S matrix. But actually, since we know this weak rotation, how to move particles along edges, what we can do is get to the configuration where they are both above by moving it up through a sequence of 2 mirror transformations or 3 mirror transformations. The red guy would end up to the left or to the right, and the difference should be an S matrix, and this motivates axiom 2. Then what's nice is that we can solve these bootstrap equations. We conjecture these bootstrap equations, we can solve them at any value of the coupling, and the result is that the square root of the pentagon, that pentagon transition is roughly a square root of the S matrix of the Flux-Tube. And as we said, multi-particle states can be obtained by a factorization, and they are more or less products of single particle states times some matrix part, because in general these particles, they have indices. For example, if you have two scalars, there are two SO6 indices and two SO6 indices outgoing. So there is some dynamical part, that is this part, and then some simple matrix part that is actually rational and independent of the coupling. Okay? Okay, so this is basically the end. So this provides a solution model, some caveats that I'm going to discuss in the next point. That we don't, I'm not claiming that we understand everything, but I will tell you explicitly what we do not understand yet. But it provides a representation for the scattering amplitude, or for the Wilson loop, that should hold at that holds at any value of the coupling constant. So now we can take this representation and compare it with weak and strong coupling results that are known in the literature. For example, the scattering amplitude that is given by this Wilson loop, at strong coupling, a Wilson loop is given by a minimal area surface that ends on the polygon in question. So it must be that this partition function object becomes the area of a minimal surface at strong coupling, which a priori is totally not obvious. But on the other hand, when we first derived the area of this minimal surface, which is a purely geometrical problem, we were quite puzzled by the outcome, by the final result, because the final result of this purely geometrical problem does take the form of a partition function. So it was begging for such an interpretation, and in fact, in the original OP papers that we wrote, we were exactly, one of the main motivations was the fact that the final result took that very inspiring form. But we were not being able to do it very precisely until now, and the point is that what happens is that all these pentagons become 1 plus something small, they exponentiate, and this result becomes exactly the exponential of a minimal area surface. And then we can go to weak coupling, and to make the story short, I can just state that we checked against all available data in the literature, and not only it works, but at very high loop order, like some 4 loop results still unpublished, not only it holds, but it helps fix all unknown constants in some integral representations. So it also works nicely at weak coupling. Now, not everything is done, and now I'm concluding. So for example, so far I did not distinguish exactly between scalars, gluon, gauge fields, what kind of excitations we are discussing. But actually, I was relying strongly on this mirror transformation, and we do not control it for fermions. So for fermion excitations, we know the spectrum exactly, and we do not know how to implement weak rotation. Okay? However, we look at the transitions for scalars and gluons. We have some experience working with the spectrum. We can more or less find out what we should tweak to get the fermion one. So we have a guess for it, even though it's not as well motivated. And it went through a lot of checks. We are able to compute the matrix part on a case-by-case study, but we do not have a very general expression, a very general analytic expression. So we can compute it. We did compute it up to, say, 8 particles or something like this, but we do not have a general N formula. But in principle, we show that it can be solved uniquely. And then, once we have all the transitions, or a large number of transitions at least, it would be nice to think what's the best way to plot this amplitude and to understand this amplitude at any finite coupling. So more ambitiously, does our partition function, this object, where all the ingredients have a nice interpretation in terms of this Flux-Tube, does it resum into something nice from the integrability point of view? Is this some nice object, like some free energy of an integrable model? Is there some nice object that resums, that does the resummation for us and that does not oblige us to put in the computer the first 100 states? It's not necessary. Even if it doesn't, we should be able to plot the amplitude nevertheless. But at strong coupling, it does. That's what I was saying before. It is exactly the Yang-Yang functional and its associated TBA equations, which is, of course, very exciting and raises great hopes for finite coupling. I think I'll stop here. Thank you very much.
Questions? Massimo?
Do you expect independence of the tessellation of the polygon by different cuttings, or?
Okay, nice. So indeed, given a polygon, I start with this tessellation, right? But now, as I deform the polygon, at some point, this red line could, for example, hit this cusp or go here and so on, right? So it would change, and I would need to change my tessellation. So for a given configuration, I find the tessellation and I expand it in this channel, okay? But then you could ask, okay, in the final result, what will be the mechanism that will tell me that as I'm deforming the polygon, the tessellation will change, but the result will be smooth and so on? And that's actually quite exciting and quite fun that you asked this question this morning, because at strong coupling, we know what's the mechanism that does this. We know what's the mechanism in this free energy that rearranges the result and that changes the tessellation from one tessellation to the other. And technically and mathematically, the mechanism is exactly wall crossing that we heard in the very first talk. So there is some wall crossing mechanism in terms of Stokes phenomena, and it rearranges these tessellations. So it would be nice if at finite coupling something like this would also take place.
Come on.
If you consider geometries which have fundamental domain, like annulus geometries, and go to dual channel?
No. The short answer is no, we did not. There are other natural extensions that we could do. We could, for example, identify the first edge and the null edge, for example. This would be like considering some annulus, where we have 2 concentric Wilson loops and the state goes around instead of starting and ending. That we could in principle do, but of course there's no data to check against, and it should work. But
Well, I was going to ask what happens if you move to different configuration where you expect that strong coupling to have different worksheet dominating computations.
so here we start with a configuration like with a surface like this. It's not disconnected, so we don't
It's like
expect the two surfaces to become disconnected. In the case that I said after, it could happen.
Yeah.
I don't know. But it will be first order, so we will not see, I think.
One last question. So let's thank the speaker again.